Good afternoon and welcome to MOS Live, everyone. Today we're talking with Museum of Science educators all about lightning. My name is Emily, my pronouns are she, her, and I'll be keeping an eye out for all of your questions today. Thank you for those of you who are tuning in on Facebook or YouTube, but please note that we are not able to share your comments with our educators from those platforms. For everyone here on Zoom, just press the Q&A button at the bottom of your screen to submit your questions. Don't forget to include your name and age if you'd like a shout out. If you'd like to see captions, you can click on the closed captions button at the bottom of your screen and select show captions. I would now like to invite my educators to come on screen, introduce themselves, and we'll get started.
Chuck, you're first.
Okay, I will start. My name is Chuck. I use he, him pronouns. And my favorite fact about lightning that I think is a really cool fact is that the Earth is not the only place where lightning happens. It happens, for example, in the atmosphere of Jupiter.
Hi, everybody. My name is Matt. I also use he, him. And my favorite thing about lightning is that one of the ways we study it is by shooting rockets at thunderclouds. Now, that is a job.
And hi, everyone. My name is Megan. I use the pronouns she, hers. And my favorite thing about lightning is that when it occurs, it can break down the nitrogen in the air and actually return nitrogen back to the soil and help plants grow, which is pretty cool.
Great, thank you, everyone. So to get us started, could you all just kind of explain what makes lightning happen? How does it form?
Sure. Let me start with a little bit of basic, and then Megan and Chuck can sort of pick up the rest. One of the things to understand about lightning is that lightning is a kind of an electrical current. And any kind of an electrical current is a flow of tiny particles of matter that we call charges. There are negative charges and positive charges, and both can make up currents, but typically it's the negative ones that we experience the most. So when you experience a lightning bolt, you're seeing a massive flow of negative charges, typically from the earth to from the cloud to the earth, although that can reverse itself. And maybe Chuck or Megan would like to tell you more about how those charges get there.
Mm-hmm. Well, charges get there because of thunderclouds, basically. It's a very interesting subject of research right now, how exactly a thundercloud gets its electric charge. And it seems to have to do in large measure with when ice forms in the upper parts of thunderclouds. Now, when thunderstorms happen here in the summer, we might not think of it as being cold enough for ice or snow, but believe me that in the upper parts of those thunderclouds, there is a lot of ice and it's rubbing up against each other. And it's the collisions of snowflakes and the ice up in the higher parts of the cloud that seem to electrify the cloud and develop tremendous amounts of electric charges, those positive or negative little particles that Matt was talking about. And if you get enough of those in one place, they can actually break down the resistance of the air. Now, air tends to block or resist electric current flowing, which means you have to get a tremendous amount of electrical charge either on the spot on the earth right below the thundercloud or up in the bottom of the thundercloud. When you get enough of a voltage difference, and voltage difference is simply a measure of the electrical potential or the kind of force that any particle would have within an electric field. When you get enough electric force going between the area at the bottom of the cloud and the ground, you will get a current start to develop, and then electricity can flow. Basically, makes a wire out of the air, and then it can start to flow between the cloud and the ground.
And just to add on that is that very simply, there's charges that are positive and negative, and opposite charges like positive and negatives attract, and like charges, like negative and negative, will repel one another. And that is sort of the basics of those charges building up and either moving toward one another or moving away from one another that Chuck was talking about.
Thank you. Harrison, age 5, asks, how many different types of lightning are there?
Let me start that one off. That can depend a little bit, Harrison, on what you mean by your question. For example, some people might say the different kinds of lightning are lightning bolts that go from the cloud to the ground, and that there's different kinds that go from the ground to the cloud, because that's true. So you might be defining that they're different based on what direction they're going. There's also kind of unusual lightning bolts that come up out of clouds. But you might also be referring to some of the popular names people sometimes come up with for lightning. Heat lightning, sheet lightning, ribbon lightning. Those are usually all the same kinds of lightning bolts, but they create different kinds of optical effects depending on how you're experiencing them. So for example, heat lightning is often a reference to when you see light flashing in clouds, but don't see a bolt. And the reason that happens is because a lot of lightning actually fires inside of clouds or between clouds. Very little of it actually gets to the earth. Megan or Chuck, do you know of other examples of kind of popularly named types of lightning?
There's something weird called ball lightning or Kugelblitz, which you might have heard about, and that's not lightning in the specific sense. That is, it's often been observed as a result of lightning bolts. You have this what's called plasma, or kind of electrically charged gas, pockets of which may develop as a result of a lightning bolt, and it's been observed to drift through the air and collide with things and sometimes disappear with a bang or something like that. So that's just one of a kind of an unusual effect that's associated with lightning, and I've never actually seen it. But I would just go back to the what Matt was talking about, the kind of lightning that is virtually the same. It's a current from one place to another, but seen under different conditions from different distances and occurring from different parts of the cloud that may make it look different.
Thank you. Prisha wants to know, why does lightning come only when it's dark? So can we talk a little bit about maybe what we see when we see lightning?
Well, lightning is certainly more visible at night. You can see lightning from 100 miles away, whereas during the daytime, you might not notice it until it's very close. And then, of course, you hear the thunder and you realize it was a lightning bolt. But it's more noticeable at night. In fact, a lot of our recent thunderstorms have occurred in the evening hours. Thunderstorms tend to be most numerous when they occur in the late afternoon, evening. Some of them can bleed over into the nighttime side, but it's really, it can be observed if you're looking very carefully, day or night. Maybe somebody else can talk more about that.
Yeah, I mean, lightning is also coming from clouds, right? And clouds are going to block out that sun. So when those thunderclouds are going to be rolling through, they're going to block out some of the sun during the day. And that might also be how you're sort of perceiving it starting to get dark just before those storms are occurring. It's just you're not getting that sunlight anymore.
And lightning can create sort of side effects that can be very difficult to see in daytime. For example, there's a delightful effect called coronal discharge that you often see on the branches of trees or the tips of lightning rods right before a lightning bolt fires. And it looks like a faint glow. A more common name for it is St. Elmo's fire. That's typically pretty hard to see unless it is very dark.
Thank you. April age 9 wants to know, is lightning always with thunder?
Yeah. They're a pair. So thunder's only going to occur when lightning occurs, and that's really because of what creates thunder. So when lightning occurs, that air is getting really, really hot, and so it's expanding and it's pushing on the air next to it, and it's pushing on the air next to that, and it's sort of just pushing through the air as it goes, and eventually reaches your ear and vibrates your eardrum, and that's when you hear thunder. So it's really when that lightning occurs, the air is getting very hot, it's starting to expand and vibrate, coming to your ears, and that's that thunder. So thunder can't really occur without lightning. Now you might hear thunder and not be able to see lightning, and that's usually just an indication, or actually you can see lightning but not hear thunder. Is that usually how it goes, right? That's just because it's the light is going to get to you a little bit easier than the sound, but they're all sort of a good pair together.
That heat lightning that I think Matt was talking about is an example of where you will see a flash in a thunderstorm, maybe 50, 60 miles away or something like that, a long distance away. That is too far away to hear the thunder, but believe me, if you were closer to that lightning bolt, you would definitely hear thunder. Anytime you get the tremendous heating of the air up to 90,000 degrees Fahrenheit in a lightning bolt, and you get it expanding explosively like that, you're not going to avoid having a huge sound wave go off of that from all the air that's been heated and disturbed.
Thank you. And while we're talking about heat, Dennison, age 5, wants to know, how hot is lightning?
So a rough estimate is it's about as hot as one of the outer layers of the sun, you know, thousands of degrees. To give you a sense of how hot it is, some of you may be keeping up with some of the current events from California and Colorado, where they're struggling to contain the destruction of hundreds of wildfires that are happening. And many of these wildfires were in fact started by lightning. That combined with the fact that they're going through a drought, the wood is already very dry to begin with. So when lightning strikes the ground, if it strikes a tree, some of the lightning's energy turns into heat energy, and that can cause those trees to burn quite easily.
Can even cause a tree to explode because any of the sap or moisture that is inside that tree, it's so hot that it gets instantly turned into steam, and the steam pressure just blows the tree apart.
Wouldn't want to be near that tree. Thank you. So we have a couple of questions here, I think related to lightning safety. For example, Jonathan and Noah both have maybe been to our museum before and have noticed that perhaps a cage is a good place to be during a lightning storm. So can you talk a little bit about that?
Yeah, not everybody is maybe like the Museum of Science and has a giant bird cage that a human can fit inside of. But luckily at the Museum of Science, we do, and that's what we use to demonstrate what is sort of safe, or where is safe to be during a lightning storm. So the first thing you want to do if a lightning storm rolls around is that you want to find shelter. That's your first choice. So something with a couple walls around you and a roof over your head. So your house, your apartment, even the Museum of Science are all safe places to be during a lightning storm. Now, if you get caught out maybe at the park and you drove to the park or the beach and all of a sudden lightning storm rolls through, you can hop in that car, and your car is certainly a safe place to be during a lightning storm. And a lot of folks believe that the reason for that is that cars have rubber tires, and rubber is an excellent insulator, so it's really great at stopping moving electric charges. That's true, but as Chuck mentioned earlier, air is also a really great insulator, and the lightning bolt can still travel through miles and miles of it to get to the ground. So the real reason why you're safe in a car during a lightning storm has nothing to do with those rubber tires, and it has everything to do with the metal frame that's around you. And those electric charges will actually move through the very outside of the metal frame and down into the ground with the help of something called the skin effect. And that's what we talk about, and that's what we demonstrate at the museum with our giant bird cage. So if you don't have a giant bird cage at home, don't worry. You can use your home or apartment or Museum of Science or even a car to stay safe.
Mhm.
Awesome, thank you. And Faith, age 9, asks, why is lightning hot? We've talked a lot about heat, so maybe why is lightning hot?
Where does that heat come from? Do this. Take your hands, rub them together really fast. What do you feel? What does it feel like? It feels hot, right? Anytime you get, that's called friction. When things rub together and are in contact with each other, when they're moving fast past each other, the energy appears as heat, and that's friction. The same kind of thing is happening with the lightning bolt going through the air, the electric current passing through the air, but on a much larger and much more intense scale. You got a tremendous number of electrons, which all at once are moving through air at a significant fraction of the speed of light, and there's a lot of them. And so a lot of electrons moving fast will heat the air almost instantly to tens of thousands of degrees, as Matt said, temperatures that are comparable to some parts of the sun. And so it's a tremendous amount of heat all at once, but it doesn't last very long. The typical lightning bolt that you see, it'll maybe flicker 50 or 100 times, but it's over. Each passage of the lightning is over in a fraction of a second. So it's a very quick but very intense heating.
And can I just say, Faith, thanks for spending the day with us. She was also at my flight program at 1 o'clock.
Terrific.
That's awesome. It's basically a day at the museum, right? So another question here. I think someone mentioned that lightning doesn't only happen on Earth. Where else can lightning happen?
Lightning can happen on Jupiter or any of the gas giant planets of the solar system. People talk a lot about Jupiter because it has a lot of energy coming from inside. There's a lot of heat energy coming from the inside of Jupiter. There are very strong winds that blow back and forth at 700 miles an hour or higher relative to each other. They're much faster than any of the winds on the Earth. And all of that energy and interaction creates a great deal of electrical charge separation, meaning that many billions of volts of electric charge develop here on the Earth in a typical thundercloud, but even more in the case of Jupiter, where there's a lot more energy of motion of different air masses and probably crystal formation, much like ice, which will create large amounts of charges. So you can have tremendously long lightning bolts, hundreds of miles long, in the atmosphere of Jupiter, and in the atmosphere of Neptune as well. Has the particular meteorology of Neptune results in what we think are tremendous amounts of lightning bolts, maybe even more so than Uranus, which is often considered to be a sister planet of Uranus, of Neptune, because it's the same size, same mass, and so forth. But many places, and it's even plausible, although I don't know if this has actually ever been measured, that dust clouds on Mars would develop lightning bolts. That certainly happens in volcanic clouds here on the Earth. When you have volcanic eruptions, you also have lots of lightning. And you have very intense dust storms on Mars. Certainly plausible that there could be lots of lightning there as well.
Hi, Chuck.
Thank you. All right. Then we have a question. Are fish affected when lightning strikes water?
Actually, Brendan did some research on this recently. Apparently, not as much as was thought. You can have some fish kill, close to where the lightning strikes, but they're actually protected by something that's a little bit like the skin effect that Megan was teaching about earlier, a skin effect that's based on their own bodies. Another thing going for them is that when lightning strikes the water, it diffuses and spreads out in every direction, so it weakens quite quickly. Now, since somebody was mentioning lightning safety earlier, it's still absolutely worth pointing out that being in the water is a pretty bad place to be during a lightning storm. The water that we typically swim in is usually very conductive because it'll either have salt in it if it's the ocean or chlorine in it if it's a pool. So electric currents like lightning will flow through it very easily. And the big thing is, even if it doesn't kill you by stopping your heart, which is what most people die from if they're struck by lightning, it doesn't take that much to knock you unconscious. And if you go unconscious in a pool, of course, you're at risk of drowning. So great safety tip: if you're in the pool, in the ocean, lightning storms coming, get out of there.
All right, you've inspired Gwen to ask the question, why does your hair stick up when lightning is near?
Yeah, this is a demonstration that we also do at the Museum of Science with our small Van de Graaff generator. One thing is, if your hair ever is standing up while you're outside and you think it's because lightning is near, I think it's definitely due time to find some shelter, because it's not necessarily a good sign. What's really showing there is that you have a lot of like charges building up on could be on individual strands of hair. And like I mentioned earlier, like charges are going to repel one another. And so those individual strands of hair with all like charges will start to actually repel one another and spread out, as you might sort of see in pictures or may have even experienced at the Museum of Science. I know we do have some equipment that sort of allows us to demonstrate this. Matt, do you have something to show?
Yep, and I can improvise that. Megan, do you mind explaining what's going on? Unfortunately, I don't really have the hair for this, so I'm going to have to use my COVID mask. And yes, I'll clean everything really well. But do you want to explain how it works? I'll set it up.
Sure. I don't think I know your equipment quite as well as what's in the TOE, but
it's a negative machine. So.
Oh, awesome. Okay, so Matt's going to turn our machine on. Excellent. And so right now, as that machine is on, it's building up a bunch of negative electric charges on the very top of that dome. And the mask, I would imagine, also has those negative and positive charges in it. It's nicely balanced. And then you can see that mass very quickly pushed away or repelled from the Van de Graaff. Maybe we can see it again. Excellent. So you can see those like charges were building up on the dome and eventually repelling the other negative charges that are also on that mask.
Mhm.
And so that can just certainly not stay up on that dome once it's on. There it goes. So again, a great example of those like charges repelling one another. So those negative charges were building up, and eventually so much so that it repelled the mask off the top of the dome.
Yeah, our safety folks probably would not enjoy me watching me throw my mask around, so let's not mention it.
Well, somebody also mentioned St. Elmo's fire, I believe, which is what also called corona discharge. That's the scientific name for it. But that is the accumulation of this electricity when the thundercloud is coming over ahead with its big concentration of electric charge. Then that positive charge on the earth is trying to get up toward it. And you've got an accumulation of positive charges at the top of every tall thing. Anything that conducts electricity will have all of these positive ions, or depending on the type of electricity present in the storm, negative. But the point is, it's all one kind of electricity. And it's all trying to not only get up to the cloud, but trying to get away from itself. So you got this buildup of electric charge particles, and they can cause the air to glow with that faint glow called St. Elmo's fire. And the same thing happened with Matt's Van de Graaff generator there. You had a whole bunch of electric particles that were building up, trying to get away from each other, but the air was kind of holding it in. But they all repel, and they end up repelling the mask.
If you do come to our Theater of Electricity, you can often see that St. Elmo's fire forming around the tips of some of our props just before the lightning strikes. So look for it when you come.
I always thought that was very cool to see. So I think this will be our last question, kind of a good one to send us off. Is it true that lightning only strikes one place, or what am I trying to say? Is it true that it only hits one place ever? It doesn't repeat the same place?
That's not true at all. As a matter of fact, the top of a tall building like the John Hancock Building in Boston, or the Prudential Tower, or the top of a TV tower can be struck, or us, can be struck dozens of times in the same storm, which is why it's important not to be the tallest object around. If you're the tallest object around, then that is where the electric particles that are trying to get up will concentrate and make you have a great voltage difference between you and the cloud. So you don't want to be the tallest object around. You also don't want to be near the tallest object around. You might think, I'm safe here because I'm standing underneath this tree in a thunderstorm. What's going to get struck, me or the tree? Well, the tree is mainly, but as that electricity from the lightning bolt runs down the tree, some of it can branch over to you on the way over to the ground. So that's probably not a good idea either.
The origin of that story is almost that lightning only strikes something once, is almost certainly that in the past, most of the things that lightning would strike, it would destroy. So they weren't around to strike it a second time. But if something is robust enough to take a lightning bolt, it can be hit, many, many times. In fact, in the early 1900s, when physicists were starting to really study lightning and measure it, they wanted to be someplace where they could get lots. So they set up their labs up in the upper floors of the Empire State Building, which to this day gets hit dozens of times a year. And as I mentioned, an even better solution now is that they actually shoot rockets up into a cloud with a long grounding cable, because that way they can get the thundercloud to strike the rocket and almost get lightning anytime they want it during a storm.
Wow, thank you all for that. So I do know that we have some unanswered questions, but we're out of time. So I'd like you all to wave and say goodbye.
Thanks for coming.
Hi, everyone. Stay safe.
Thank you so much. And thank you all so much for being here today. We so appreciate all of your great questions. To check out more programs, please visit the website mos.org/mos@home, or follow us on social media. And if you've enjoyed today's presentation, please visit the website that I'll put up on screen shortly to support MOS at home. Thank you, everyone. Enjoy the rest of your day, and we'll see you next time.